Welcome, everybody, to the latest episode of Stars, Cells, and God. This is the podcast where we explore the latest discoveries taking place at the frontiers of science and describe how those discoveries provide evidence for God's existence, God's nature, and the reliability of Scripture. My name is Rana. I'm a biochemist and a Christian apologist, and I work for an organization called Reasons to Believe. If you want to know more about Reasons to Believe, go to our website, www.reasons.org. Also, you can follow us on social media, RTB_official. And then last but not least, please go to our YouTube channel, Reasons to Believe, and use the subscribe button so you can access great content that we have on a wide range of questions dealing with science and the Christian faith. Also, use the notification button so that you can be alerted the next time an episode of Stars, Cells, and God drops. Okay, well, I'm joined in studio today by Dr. Hugh Ross, who is an astrophysicist and also a Christian apologist and the founder of Reasons to Believe. And Hugh, you've got a great discovery about human migrations and how that connects to the Genesis 1 to 11 creation story. And then I'm going to be talking a bit about Maxwell's demon or Maxwell's demons and how these actually appear in certain biochemical systems.
Well, Maxwell is one of my heroes. Demons, not so much.
Yeah, there we go.
Okay.
There we go. All right. Well, Hugh, why don't you start us off with a discussion
Sure.
of your work?
Well, I'm about halfway through writing a book about Noah's flood. We're actually writing a full-length book on Noah's flood. And I just finished writing the chapter on dating Noah's flood. And it's not easy to come up with an accurate date for Noah's flood. In fact, that's a point I make, is we can come up with an estimate. What we do see in Genesis is that it took a year for the flood waters to recede. And for it to take that long, there would have to be huge amounts of melting snow and ice. So I believe that Genesis 8 is telling us that Noah's flood took place sometime during the last ice age. Now, that doesn't give you an accurate date. That's anywhere from, say, 14,000 to 125,000 years ago. But what you see in the chapters that follow Noah's flood is that humanity was commanded by God to multiply and fill the earth. And Genesis 11 records that they were not doing that. They were staying in one region. And God basically came down and gave them different languages and scattered them over the whole face of the earth. And when you read Genesis 10 and 11, it seems to suggest that the scattering was quite pervasive and fairly rapid. So I went into the scientific literature to see if there's support for this. And I was reading these review papers on how do we date the arrival of the first humans into Europe, the Americas, Australia. We know that humans were present in Africa and the Middle East and parts of Asia, but what about the dispersal into all of Asia? And what I noted about these review papers is that they were looking for dates that were consistent. And basically, they talked about 4 dating methods, and it's something I've written about before. And the 4 are, dating human remains. So you got the remains of human beings, the bones particularly, and you can date those. You can date the artifacts that are clearly associated with anatomically modern humans. And anatomically modern humans were involved in cooking their food almost right away. So the other piece of evidence they look at is food preparation. What's the date we got for food preparation? And then last of all, the genetic evidence. The first 3, typically you're using carbon-14 dating. And they were claiming that if they got a big enough sample, they can push that back to 50,000 years ago.
Yeah, with things like accelerator mass spectrometry, things like that.
Yeah, you need a pure sample. It needs to be a fairly big sample to get it that early. Yeah. Getting back to 40,000 is not a problem, but 50 is a stretch. But they have data that can take them back that far. And what they're looking for are dating methods where they say, well, we have reliable dating methods, And they're not showing any evidence, and then they do show evidence. So they always want to insist that they got reliable dating methods that go earlier than the earliest positive indication. So they got both a negative confirmation, a positive confirmation. And when they did that for Europe, the dates were amazingly consistent. And so, because they had all four, they had the human remains, you got the artifacts, and probably the latest one was that they were actually able to date that humans were doing sophisticated food preparation in Greece that goes back 40,000 years. You know, until a few months ago, the earliest date they had was like 33,000 years ago, but they pushed it back to 40. And this is where they got evidence that humans were harvesting grains, soaking them, and boiling or roasting them in order to, and then how they were actually using grains that would be poisonous for human consumption if eaten raw. But if they're boiled and roasted and ground, then they're safe to eat. So they thought that was a really good indicator of the fact that, hey, they really were involved in this. So that dates 40,000 years ago. The genetic dates were coming in at 42 to 44,000 years ago. And then the dates that they get for human artifacts were 40 to 45,000 years ago. And human remains were between 40 and 44,000 years ago. So the bottom line is 40 to 44,000, and probably closer to the 44 than the 40. But you know, that's a secure date. And then they said, okay, let's do the same in Asia. And let's go to parts of Asia where you would need significant migration. So, for example, Eastern Siberia. You know, it's a long walk from the Middle East to get to Eastern Siberia. Or Southeast Asia. So looking in the Philippines and Borneo, Vietnam area, and looking for, and they did the same four techniques there. They did note there that the genetic data had fairly big error bars. When they only looked at human remains and artifacts that are identified with anatomically modern humans, they did not find any early evidence for food preparation. But those dates, again, were coming in at about 40 to 45,000 years ago. One was saying maybe 46,000 years ago. The genetics was like, 40 to 50,000 years ago. So, and then what caught my attention was there's been a huge revision of dating for Australia. And there were two review papers that basically made the point, hey, there's evidence that humans, cited evidence in the scientific literature that the humans were in Australia 65,000 years ago. And you're probably aware of that famous Gymnian rock shelter where they were saying 58 to 75,000 years ago. The reviewers basically discounted all of that because they said we've actually been able to find carbon remains associated with the thermoluminescence dating, basically showing that the thermoluminescence dating was pushing the dates back way earlier than was legitimate. So, for example, they were finding these circular engravings in the Gymnian rock shelter in Australia, and that's been in the literature 58 to 75,000 years ago. But in the very same layers in which the engravings were found, they found some carbon, radiometrically dated that, and those samples are coming back 100 to 3,900 years ago. So basically making the point that the thermoluminescence was off by a factor of about 20 times. And they were able to show that in every case, the thermoluminescence and optical luminescence dates were pushing it back way too early. And I think for obvious reasons, the method is based on how much exposure the samples are getting to solar radiation. And if you don't know how long it's been buried, you're going to get a big systematic error. So, but fortunately, they were able to find carbon samples in the same remains and basically said, okay, Gymnian, we have nothing old, but there's 26 other sites in New Guinea and Australia where they were able to recover carbon in the human remains. And those dates came back 40 to 47,000 years ago. which is something that you'd think would be reasonable if you've got evidence for humans in Southeast Asia, 40 to 46,000 years ago. It's not that difficult for those humans to make it into Australia. And we got a map here to show people, because when you're living during the last ice age, sea levels are as much as 390 feet lower than they are today. And so throughout the entire ice age, you've got this continent that they call Sahel, and it's Australia and New Guinea and Tasmania, all as one contiguous landmass. And so Australia is a bigger continent during the last ice age because of lower sea levels. And likewise, you notice that Borneo is not isolated from the Asian mainland. You got land joining Borneo, Java, Sumatra, to Cambodia and Vietnam. They call that region Sunda. And there is some water that separates the Philippines from Borneo, but the water separation we're talking is only a few miles.
Yeah.
And so humans can actually see, hey, there's land over there, and they can use crude boats to get over there, because we do see evidence for human habitation in the Philippines just as early as we see it in Borneo. But that is significant, because that means if humans are able to go from Borneo into the Philippines at about the same time, you also notice in this map is that you got short water distances between Sunda and Sahel. There's several different migration routes,
Right.
where you can basically say, hey, I can see land over there. You can use a crude boat to get over there. And so it's not surprising to me that we got roughly the same dates for humans colonizing Sahel as we have humans colonizing Sunda and the Philippines. Today, it'd be a major job to try to go from Southeast Asia to Australia because the Timor Strait is quite wide. But during the last ice age, that would have been a narrow strait, and humans can get there. But I think the thing that impressed me, Fuzz, is that here you got these thorough. You got 4 different dating methods, and they're being used in Europe. And by the way, they're seeing it all over Europe. It's not just in Italy. Italy and Spain is where they got the most data, and France, but they're actually seeing they got new data that basically shows that humans were getting into England just as rapidly as they were getting into Italy and Greece. So once again, of course, back then, you got a land bridge joining France to England. And so we have dates that are basically 42,000 years ago for humans in Britain. And I think what impressed me is this really does seem to support the interpretation of Genesis 9, 10, and 11, that there was a moment several generations after Noah's flood where God aggressively scattered humanity over all the continents of the earth, with the exception of North and South America. That was later. That's about 16,500 years ago, where you have the first undisputed evidence for humans in North and South America. But indeed, what we see is that all of Eurasia and Africa was fully inhabited somewhere between 40 and 45, 47,000 years ago.
Right.
And it seemed to be taking place simultaneously over the entirety of Eurasia.
Right.
So that would support that particular interpretation of Genesis. And if you actually look at what the early church fathers were writing and people in the Middle Ages and the Reformation, that was the most common interpretation of those chapters in the book of Genesis. And now we got the data that basically sustains that, yes, that is the most reasonable interpretation of the text, and we now got the science to support that interpretation.
Yeah. Now, the models that I've seen, at least, and these are previous models, would say that the migration, out of Africa would have been, in the 50 to 60,000 year range, and that the route of migration would have taken advantage of this coastal superhighway, right? So that because they're moving along the coast, humans are moving along the coast, there's a plenty of resources available, and the landscape is very similar. and and they may have taken, some small groups may have broken off and have migrated up rivers and things like that. And that the idea was that probably Asia was occupied first, and then you'd have a back migration into Europe at about 45 to maybe even 50,000 years ago. I'm seeing some reports that small groups of humans may have been in Europe even earlier than 45,000 years ago. So that's kind of the and then there would also have been a migration into Australia, right, from Asia. Asia was kind of the place where humans went first and then spread from there.
Well, these authors are making the comment, yes, you do see earlier dates for Africa, the Levant, the Near and Middle East. But what I was focusing on here is when do we actually see humans in the extremities of Asia?
Right.
Not just, the Near East and Middle East part, but in the extremities of Asia, the extremities of Europe, and into Australia.
So that gives you, in effect, you might say a minimum date for when the flood would have taken place. And then the maximum date would have been when you've got evidence that humans began that migration. So you're able to kind of bracket it, right?
Yeah, that's all I'm saying. We can get a bracket. We can't get an accurate, precise date, but we can get a bracket saying it has to be earlier than this.
Yeah.
And what this date is telling us is not the date for Noah's flood. It's the date for the dispersal of humanity after Noah's flood.
Right. That's
when you look at Genesis chapter 11, you notice there's several generations between Noah and the dispersal event. And exactly how many generations, that's open to interpretation because there's a consensus.
Right.
None of the genealogies in the Bible are complete.
Yeah.
And so, you got some leeway there as to how much time goes by, but certainly you'd have to conclude that Noah's flood would have had to take place previous to, say, 45,000 years ago. And you say, well, how much more previously can it go? Well, I believe that Genesis 8 is definitively telling us it took place during the Ice Age. And so you could go back 120,000 years ago. You're still in the Ice Age. Some have argued maybe you can go back to the previous Ice Age. But it is interesting that you do get at least a range of reasonable dates by using these methods.
Right. Because, this is a pretty impressive study. I guess the one, if you might want to call it weakness or maybe limitation, is they are relying on carbon-14 dating. And as you're pointing out, that you can push it maybe to 50,000 years ago. But if you're looking at events that may have happened a little bit earlier, that technique is going to be, silent about that.
Well, they do make the point that if you're looking at other dating methods like thermoluminescence or uranium thorium precipitation or optical luminescence, you're dealing with really big systematic errors, and explains why there's such a disparity there.
Right.
But they did bring in the genetic dating method, which is not based on carbon-14.
Right.
And they said, where you got a significant population study that you can do, they said it's interesting that it's consistent with these radiocarbon dates. So that's why they're saying we're suspect of earlier dates.
Right.
So they're basically discounting the earlier dates. But again, they're focusing on, okay, where do we see humans being broadly dispersed?
Yeah.
They're not addressing the first humans. We're not talking Adam and Eve.
Right.
We're talking about the dispersal event that's described in Genesis chapter 11.
Yeah. No, this is a really interesting study. It's, inching us towards a much more robust,
well, it's the
insight
first time
into Genesis
I've
1
seen
and 11.
What impressed me, the review papers were these are independent groups of researchers doing a review spread over a 5-year period, but they're all coming up with the same answers. So the fact that we see a consistency in their conclusions, and the fact that we see a consistency on 3 different continents, I think really does give support that, hey, we're talking an aggressive, rapid dispersal. And, that would be a signature of the hand of God.
Yeah, well, I mean, minimum, what it's saying is that the biblical text is fully compatible with what science is discovering. And you're right, that very rapid migration is, to me, really odd, right? That the fact that you're seeing humans moving that quickly.
Well, it's especially odd when you see them moving into places that are not climatically optimal. They're going into Australia where there's a real problem coming with the water that you need, so it's a harsh environment. Northern Europe is harsh. You go to eastern Siberia, that's harsh. So the fact that we're seeing humans tells us, hey, this is something that we wouldn't expect. And in terms of where we might go next, well, I think it's clear that you have to be at certain times during the last ice age where you wouldn't have a climate that would make migration almost impossible. And so, as I look at the ice core records, there's certainly episodes during the last ice age where this could happen. There's other episodes where it couldn't happen, but you can wind up with 20 episodes where it could happen.
Yeah.
So it's like we're still looking at an estimate.
Yeah.
We're not looking at an accurate date. And I don't think we ever will come up with an accurate date. But we are coming up with something that's biblically consistent.
Yeah. Really interesting stuff.
Yeah, well, thanks.
Yeah.
It was fun doing this.
Yeah. Okay, well, let's move on, and I'll go ahead and talk about the idea of Maxwell's demons in biochemistry. And just for a way to introduce the idea of Maxwell's demon, as a scientist, of course, you're very well aware of the important role that thought experiments play. Oftentimes, they can be used as a device of the imagination just to begin to create scenarios that lead to hypotheses that can then drive scientific advance. Other times, they're used as ways to kind of illustrate scientific concepts, particularly for a lay audience. And so Wired magazine, I think in 2007, published an article where they listed what they thought to be the most famous thought experiments. Now, what's missing from that list is Einstein's twin paradox. But that aside, this is their list, and I'm not going to spend any time discussing any one of these experiments in detail. We don't have time for that. But these are all experiments that I think most people who have any familiarity with science would be well aware of. But the one that I want to talk about is the Maxwell's demon. And this is actually a thought experiment that Maxwell developed in the late 1800s to illustrate really the second law of thermodynamics and to speculate as to how could you conceive of a scenario where you could violate the second law. And Maxwell actually didn't use the term demon in his original description. It was just a being. But then somebody else later on used that term demon. So demon doesn't actually trace its origin to Maxwell, but to somebody following Maxwell.
Maybe somebody who had a particularly cantankerous cat, right?
Yeah, there we go. But the idea behind this is that, if you have two boxes that have gas particles that are moving around, they're going to move at a range of speeds. And the faster the particle moves, the hotter the temperature of the particle, right? And so the idea would be that if there is a opening between the two boxes, there is going to be an equal distribution of particles that are hot and particles that we might say are cold.
Right.
And so the idea behind the demon is that this is a being that is able to open and close a door that doesn't weigh anything. And by opening and closing the door, the demon can let all the fast-moving particles wind up in the left box and the slow-moving particles in the right box, or vice versa. And by doing that, you now create a non-equilibrium situation that violates the second law, right? And so that's Maxwell's thought experiment. Physicists, interestingly enough, as I learned as I read about this experiment more, actually have spent about almost 100 years thinking through this experiment, trying to come up with ways to explain how Maxwell's demon could actually achieve this non-equilibrium situation without violating the second law.
Well, you know, Fuzz, when I was a freshman physics student, we got a problem assigned to us by the professor to calculate the probability that this would work in such a way that the student next to us would freeze to death while the student on your right would be sweating buckets from heat. And that's an actual physics problem. There's a real number that calculates the probability of that happening.
Yeah.
Fortunately, the probability is relatively small.
Right. Well, in other words, I mean, you would be violating the second law, right?
Right.
Or you practically would be. Well, the solution to the problem comes from this physicist by the name of Rolf Landauer, I guess would be his last name. And he's an information theorist who argued that the way in which the demon fails to violate the second law is that the demon has to make a measurement on the particle to determine its speed, and then has to store that information to act on it, and then has to erase the information so that it can evaluate the next particle. And that process of going through these information-oriented operations is going to require energy expenditure, and the energy that's expended is greater than what's achieved by attaining the non-equilibrium situation.
Right.
So that's how you can resolve this paradox that Maxwell devised with his...
The demon can't pull it off.
The demon cannot pull it off, right? And according to Landauer's calculations, the step that consumes the most energy is actually erasing the information from the demon's memory. Now, so here we are, fast forward to a few weeks ago when a research team from Switzerland discovered that these proteins called ABC transporters are actually Maxwell's demons. Now, what they mean here is that these are not proteins that are violating the second law, but rather these are proteins that are functioning like a Maxwell's demon in light of Landauer's work, where they are recording information, storing that information, and then erasing that information to attain a non-equilibrium distribution of particles across the cell's membrane. So these ABC transporters are proteins that are ubiquitous in biology, and because of their ubiquitous nature, they most likely would have appeared in the last universal common ancestor, maybe even earlier in life's history than this hypothetical LUCA. But these are called a protein superfamily, and these proteins reside in cell membranes, and they will transport materials either into the cell or out of the cell. If it's into the cell, it's an importer. Out of the cell, it's an exporter. But in all cases, they're using energy to maintain this concentration gradient or to this non-equilibrium situation.
So you could refer to them as customs agents for the cell?
Yeah, to some degree, that's one way to look at them. And this is what's called a ribbon diagram of two different versions of these ABC transporters. They consist of 4 subunits. 2 of them are called the transmembrane domain. These are embedded in the membrane, spanning the inner and spanning the membrane, connecting the inner and the outer regions to each other, the inner region of the cell to the outer region outside the cell. And they actually can open and close to form a channel that allows the movement of materials across the membrane. The other part of the protein is called the nucleotide binding domain, and it's always found on the cytoplasmic side of the membrane. And these are subunits that bind the molecule ATP, which is also known as a nucleotide. And when ATP is hydrolyzed, it generates ADP and inorganic phosphate, but that hydrolysis reaction liberates energy that the cell uses to power the transport across the gradient. The nucleotide binding domains in ABC transporters are virtually identical. This is why they are considered to belong to the same family. However, the transmembrane portion varies widely from organism to organism and is highly specific to the particular material that it's going to move across membranes. And now the protein on the right with the pink subunit, that's actually for an importer, where that protein will bind materials in the exterior environment and bring it to the transporter so that it can deliver it into the cell. So this is considered to be part of the protein complex, though it will dissociate from the transmembrane binding domain. Interestingly enough, importers are only found in prokaryotic organisms like bacteria, whereas in eukaryotic organisms like humans, we only have exporters. And these proteins are actually very important proteins because, number one, they are one way in which bacteria acquire nutrients from their environment. But the exporters in bacteria will export toxins out of the cell, which includes antibiotics. And so there are some bacteria that have multi-drug resistance, multi-antibiotic resistance, because they have these ABC transporters that view the antibiotic as a toxin, which it is for the bacteria, and they will eject it from the cell. Well, in humans, we have these exporters as well that are sometimes used to move fats from the cell into the cell membrane or to secrete them into the extracellular space. But we also use them as a way to protect the cell from toxins. So this is really important because when people are trying to deliver drugs to patients, these ABC transporters will actually work against the drug delivery mechanism, kind of frustrating delivery of drugs. So these are biomedically very important proteins, and in fact, in humans, there might be about 50 different ABC transporters that are found. This is a close-up real quickly showing the nucleotide binding domain, and those pink regions, those little pink molecules are ATP that are bound to the nucleotide binding domains. So this slide shows the mechanism for how these work, and this becomes important to understand why these are considered Maxwell's demons. So this is an importer that would be found in a bacteria. Mm-hmm. And so you have this binding protein that is like this light green V that binds the material going to be moved across the membrane that will then interact with the transmembrane domains. And in that resting configuration, you have the two transmembrane subunits in a configuration that is opened to the cytoplasm. And in that configuration, the nucleotide binding domains will bind ATP. So when that protein binds, it will deliver that it'll cause a conformational change, so the transmembrane domains will flip the other way.
So the gate opens.
Right, and now it creates a binding site for the molecule to be transported. It's called a high affinity binding site. There's a high attraction of that protein region to that particular molecule that's going to be transported. Once that binding happens, it causes a change in the nucleotide binding domain that then causes ATP to be hydrolyzed. When that happens, it then changes the conformation of the transmembrane domains so that it now flips the binding site from the exterior of the cell to the interior. And in that configuration, the binding site is a low affinity site, which means the molecule dissociates. So you have two molecules of ATP that are hydrolyzed in order to move that one molecule across the membrane. And then it goes back to this resting configuration and the process is repeated. Similar mechanism for exporters, where again you have this case, in the resting state, the transmembrane domain is open to the interior of the cell, and then there's a high affinity site. Once that substrate binds, it causes ATP to bind to the nucleotide binding domains. That causes a change in the transmembrane domains that then create a low affinity site. The material is excluded from the cell, and ATP is hydrolyzed, and the process is repeated. So it's a this sequential stepwise process. And so what the researchers noted is that there's a superficial similarity between ABC transporters and Maxwell's demons. And this is a diagram taken from the paper where they show kind of the superficial similarity. But what they then did is they developed mathematical models to describe the transport of materials in and out, either in or out of cells. And these mathematical models expose the fact that these are not just simply superficially similar to Maxwell's demons, they actually are functioning as bona fide Maxwell's demons. And this is what they say. In this work, we propose a simple model of ABC transporters whose solution shows that they are not simply analogous to Maxwell's demons, they are autonomous Maxwell's demons. And what's happening is these ABC transporters are actually gaining information about the substrate, right? Just like a Maxwell's demon would do. And this is through the binding of that substrate to that high affinity site. That binding operation is now communicating information about that material. It's telling that transporter this is to be moved from one side of the membrane to the other. So that's the measurement, and then it's storing that information in memory in the conformation of the protein. And then when it changes the conformation and the material is moved across the membrane, the protein returns to its native state, and that is an erasure of the information that was stored. And this is where usually the ATP hydrolysis is taking place in conjunction with that step. And so this is literally a Maxwell's demon. Now, what's interesting is that the Maxwell's demon of the Landauer conception, not the Maxwell conception, literally is a molecular level machine. It's a nano machine. And in fact, this is a quote from a physicist who works in statistical physics, commenting on the work published by the Swiss scientists. And he's pointing out that these ABC transporters can be thought as simple computational devices that are employing what's called a logical AND circuitry. And this is what a logical AND circuit is. It's essentially a scenario where you have to have two inputs that are true in order for an output to take place. And the two inputs would be you have to have the substrate binding to the high affinity site, and ATP has to be bound. And it's happening sequentially, and as a result of those sequential bindings, you literally are getting a transport. So this is where things become, I think, really interesting in terms of the philosophical implications of the work.
Well, let me stop you right here, because this really, like what they're saying, these are not just analogous, they really are
Right.
Maxwell demons, in which case, according to the physicists, there should be an energy requirement to make this work.
Right.
And so have these chemists actually measured the energy?
Well, it's the ATP hydrolysis.
True, but it has to be at a certain level to make all this work.
Yes. I mean, we know how much energy is released with ATP hydrolysis. And we know you can calculate using equations of chemical thermodynamics what the energy is that is attained to maintain a gradient across membranes. If the particle is charged, it's an electrochemical gradient. If not, it's just a chemical gradient. So there are equations that will calculate that energy that's required to maintain the gradient.
All I'm asking is, did the researchers actually do the energy calculations to show that this is consistent with their conclusion that these are actual Maxwell demons?
I don't know that they did. What they did is develop mathematical models that showed that there was a measurement of there was information being recorded about the particle, stored and then erased. That's what they were pointing out. They didn't need to do those calculations because that's been well established just by the study of ABC transporters. Is that
So previous work already established that.
Right. We know how much energy is released when ATP is hydrolyzed, and we can calculate the gradients, and so you can show that you're not violating the second law, right? That there's actually a generation of heat.
So the physicists need not panic.
Right. Yes. There's nothing to panic.
Okay.
Yeah. But to me what's very intriguing about this is that this is demonstrating unequivocally that these ABC transporters are computational devices, that they actually are making a measurement, recording that information all within the structure of the molecule, and then erasing that information, and in employing a particular type of circuit known as, again, a logical AND circuit. But these are literally computation devices. These are not just simply molecules that are moving materials across membranes, but there's actually a computation taking place. And when there's a computation taking place, there's an algorithm, right, which is a set of instructions that these proteins are following. And that algorithm is actually built into the physical structure of the molecule, right? It's built into the structure of the binding sites. It's built into the protein, tertiary structure. It's also built into the way in which the transmembrane binding domains interact with the nucleotide binding domains. So that structure is really critical, again, to process that information and then to again erase that information. And so when you talk about algorithms that are physically instantiated within a physical machine, that suggests the work of a mind, right? Algorithms are a set of instructions. A set of instructions are information, and we know from experience that information is something that minds create. Instructions are something that minds create, right? And so in order for this to be an information system that is engaged in computation or engaged in an algorithmic operation, there's got to be a mind behind it, because those kind of machines we build all the time as humans, and these machines, again, reflect the work of intelligent agency. And I think you were actually with me on a show maybe well over a year ago where we talked about biochemical finite state machines.
Right, I remember that.
So real quickly, finite state machines are these machines that can exist in discrete states, and they transition from one state to another based on input. And so there's input, there is a different states, and there is the transition mechanism, or the transition that takes place. And the transition between states depends upon the state that the machine is currently in and the nature of the input. But and finite state machines, there are two types. One are what are used by software engineers to develop computer programs, but the other are actually physical machines that engineers create. And these finite state machines are all around us. One of the simplest one would be a turnstile, where there are two states, locked and unlocked, and the input is a coin and a push on the part of the person using this. And so depending upon the state of the system, the coin as the input, and whether or not the system is pushed, the system will go from an unlocked to a locked state. That is a finite state machine. And there are much more elaborate finite state machines, like the ATM machines we use to get money, or a vending machine. These are all examples of finite state machines. But the point is that these machines are mechanical computers, where there's an algorithm, and again, the algorithm is literally built into the design of the machine, right? And so what we're seeing here is an analogy between the ABC transporters and finite state machines, which are computation devices. It's just that these ABC transporters are biochemical finite state machines that are using, again, this logical AND algorithm to deploy their
Fuzz,
operation.
I think what makes your argument strong is the fact that you need both the algorithm and the machine to ensure you're getting the right export compound going out at the right rate.
Right.
You got to have it tuned to the molecules you want to get rid of, and the rate that you want to get rid of them.
Right.
And we're dealing with more than one toxin, right?
Yes.
And so that means we need to have multiple distinct algorithms and multiple distinct machines.
Right.
Which is, again, the whole point. You need a mind to explain that.
Right.
We're not just talking one algorithm and one machine.
Right.
We're talking multiple ones, and different cells are going to have different needs.
Right. In a sense, this is essentially a double watchmaker argument. You have these, again, ABC transporters that are ubiquitous, that are critical, for living systems. These ABC transporters that are, again, finite state machines, literally finite state machines, which is similar to the machines that we build. And then the second, part of that watchmaker argument, or what augments the argument, is that they also are information systems using an algorithmic information. So it's really a double watchmaker argument. And again, the idea would be, look, our experience is that these kind of systems reflect, not only, intelligent agency, but some pretty brilliant minds to conceive them.
It's quite an engineering feat.
Right, to conceive them and to design, and to execute their design. So when we see this kind of feature that defines biochemistry, to me it really is eerie and suggests there really is a mind behind everything.
And you're not going to have the origin of life without having these in place.
Right. The fact that these systems, which really are sophisticated, show up this early in life's history is again, really something that is hard to explain from an evolutionary perspective because...
And they have to be fully present in the very first life form.
Yeah.
You can't get away without them.
Well, there was an episode we did, I did it with Cy Gart, where we talked about some recent work showing that the last universal common ancestor was far more complex than anybody would have imagined, and that it shows up extremely early in life's history, arguably earlier than 3.8 billion years ago. And the researchers were saying, look, this is not a gradual accumulation of complexity. This is a very rapid emergence of a very complex system. And the ABC transporters are going to be part of that complex system, as well as a whole host of other very complex biochemical
and
operations.
You're going to need more than one machine and one algorithm.
Yes, exactly.
Right at the very get-go.
Right. So anyway, I think it's just a really fascinating discovery. Just from a scientific perspective, it really is more than just simply a novelty. It really has implications in terms of understanding fundamental biochemistry. But we're seeing more and more work that's exposing the idea that there's information that's algorithmic in nature that's really embedded within biochemical systems.
Now, has anybody in the peer-reviewed literature written anything that connects these ABC transporters to the origin of life problem?
No, not that.
Maybe you ought to do that, Buzz.
Yeah, yeah. Well, it's interesting though because a number of years ago, Paul Davies and Sarah Walker wrote an article where they basically were making the point that the origin of life research community is chasing the wrong car, right? There are dogs chasing the wrong car, because the real question is, how do we explain the origin of algorithmic information?
Right.
And they were marveling at the fact that biochemical systems have these algorithms that are instantiated in the physical makeup of biochemistry, and that this is essentially dictating the operation of these systems. And their point was, nobody knows how to explain the origin of algorithmic information. We can explain how a protein might emerge with a particular sequence of amino acids. They said that that's a relatively easy problem.
Still challenging, but comparatively.
But for the origin of algorithmic information that is then instantiated in the molecules, they're arguing there isn't a model, but that's really the origin of life problem. And so what these researchers are doing is highlighting the fact that this seems to be a ubiquitous feature of biochemical systems, and that ubiquitous feature is tied up to the origin of life problem, in that you've got to explain where the algorithms are coming from. And not only that, but then how do they get built into the design of the molecules?
Right. Because
those algorithms cannot tolerate much structural variation in the proteins. If you start varying the binding sites for the substrate that's moving across the membrane ever so slightly, and you create a low affinity site where it should be a high affinity site by just changing one or two amino acids, you now have compromised the operation of that system. So there's a precision to being able to read the information in the molecule and then to store that information and operate on it and then erase that information. It's not trivial.
Well, I hear your passion, Fuzz, and I don't know how many of our constituents are aware that your area of real high expertise is membrane biochemistry.
Yeah.
This is right up your alley.
Yeah.
So I'd love to see you write a paper that actually links these ABC transporters to the origin of life problem, because I think that'd be, and we'll see where we can get it published and distributed, but somebody needs to do it, and I think you're the guy to do it.
Yeah. Well, I mean, I actually did present a paper at a quasi-scientific meeting this summer about the idea that biochemical systems are finite state machines. And I did get feedback from our friend David Snoke, who's a physicist, who thought that was something that could actually be published as a novel insight into the nature of biochemical systems. But the theological implications are enormous. If you know. So anyway, it's my passion. I don't know how many people watching this are passionate about membrane biochemistry, but it's my passion.
I'm passionate about this, Fuzz, because I can see the potential that this has to really build the reasons to believe model in the context of the origin of life.
Yeah.
I mean, we've written a book on the origin of life. You've written a lot of papers on it. But this, to me, is a major breakthrough that I think we need to really get well.
Yeah.
So.
Well, thank you. Yeah,
Okay.
and thanks to these scientists from Switzerland who
Well,
had
let's see if
some
we
really
can carve
interesting.
out some time in your schedule, because I know we're keeping you awfully busy.
Yeah.
So hopefully we can set you free to do this.
Yeah, I'd love to.
Yeah.
All right. Well, I think we've done enough damage for today, Hugh. But hopefully everybody has enjoyed our discussion of two discoveries in science that continue to affirm the idea that God exists, that God is good, and that the Scripture, particularly the creation accounts, are reliable. And if that's the case, then the message of Scripture, which is ultimately the gospel, is reliable as well. Join us next time for Star Cells and God, and you can be notified when the next episode drops if you go to our YouTube channel and you not only subscribe, but you use the notification button. It will alert you when, again, the next episode of Star Cells and God drops. Follow us on social media, RTB_official. And then also make sure that you subscribe to this podcast using the different podcast services that are available. And then finally, I just want to remind you, the more we discover about science, the more we have reasons to believe. Until next time.